last video, I had talked about finding eigenvalues and did a couple of examples using a 2x2 matrix. And in that process, we had to solve a quadratic equation. However, what if the solutions to the quadratic equation are complex? We know that's possible with quadratics, so what happens? So let's suppose we have the solution lambda equal to a plus bi. Then we also have another complex value of a minus bi. And this comes from the quadratic formula saying the plus or minus the square root. And this over here, this a minus bi, is known as the complex conjugate, and we denote it by lambda bar. And so in general, the complex conjugate just means change the sign on the imaginary part. So let's suppose that lambda is a complex eigenvalue of a matrix A with corresponding eigenvector x. Then we have that lambda bar, the complex conjugate, is also an eigenvalue of A with corresponding eigenvector x bar. So if we have one eigenvector, we can take the complex conjugate of it to find the other eigenvector. So let's look at some examples of using this. Here I have a matrix, and I want to start by finding the eigenvalues. So I'll do 3 minus lambda, 1, negative 2, and 5 minus lambda. Multiplying gives me 3 minus lambda times 5 minus lambda, minus negative 2. We want this to be equal to 0. This goes to 15 minus 3 lambda minus 5 lambda plus lambda squared plus 2 equal to 0. So this becomes lambda squared minus 8 lambda plus 17 equal to 0. Using our quadratic formula, we would have negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Simplifying this gives me 8 plus or minus the square root of negative 4 over 2, or 4 plus or minus I. So we have our eigenvalues of 4 plus I and 4 minus I. Now let's find eigenvectors. So let's start with the 4 plus I. We need to subtract this from the diagonal. So we have 3 minus 4 plus I, 1 minus 2, and 5 minus 4 plus I. This is going to simplify to negative 1 minus I, 1, negative 2, and 1 minus I. And now, our next step was to row reduce. However, we're going to skip that and take advantage of some things. First, we know this has to have an infinite number of solutions by the way we defined eigenvalues and eigenvectors and how we constructed them. So we know this has an infinite number of solutions. So I know that as I reduce these, one of the rows is going to be a row of zeros. And then I'm going to actually leave this second row the way it is and write it as negative 2 to the 1 minus I. This gives me the equation negative 2x1 plus 1 minus I x2 equal to 0. And the reason I did this instead of the first row is because my next step is to solve for x1, which will be 1 minus I over 2x2. And if I would have used this first equation instead, I would have had to divide by a complex number, and I didn't want to do that. So I went with the one that had a real number in the first spot here so that I didn't have to worry about division by complex numbers. So now my equation for x1, 1 minus I over 2x2, and x2 is my free variable. Factoring out the x2 gives me 1 minus I over 2, 1. And we like to go ahead and multiply through by our denominator to get 1 minus I, 2 for my eigenvector. For 4 minus I, we just change the signs on the imaginary parts. So this one would be 1 plus I, 2. And now we have both of our eigenvectors. Let's look at one more. We start by finding this determinant. So we have negative 1 minus lambda 2 minus 1 minus 3 minus lambda. Multiplying gives me negative 1 minus lambda times negative 3 minus lambda minus negative 2 equal to 0. This is 3 plus lambda plus 3 lambda plus lambda squared plus 2 equal to 0. Or lambda squared plus 4 lambda plus 5 equal to 0. The quadratic formula says negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. This simplifies to negative 4 plus or minus 2i over 2, or negative 2 plus or minus I. So my lambda values will be negative 2 plus I and negative 2 minus I. I now want to find the eigenvectors, so we'll start with negative 2 plus I. This gives us negative 1 minus negative 2 plus I, 2, negative 1 and negative 3 minus negative 2 plus I. This is going to go to, we have this to be 1 minus I, 2, negative 1, and then negative 1 minus I. Once again, I know that one of these rows is going to go to 0, and I'm going to use the row that gives the coefficient of x1 to be a real number. So I have minus x1 plus negative 1 minus I x2 equal to 0. This gives me negative 1 minus I x2 is equal to x1. So when I do my vector, I put the number, or the equation for x1, negative 1 minus I x2, and then x2 is a free variable. Factoring out the x2, I have negative 1 minus I and then 1. So my eigenvector will be negative 1 minus I, 1. And for the other one, I changed the sign on the imaginary part to give me negative 1 plus I, 1. So now I have both eigenvectors.